Hi everyone, I'm Tingting. I'm going to give the talk about our paper, Algebraic Key Recovery Attacks on Reduced Round Xoofff for SAC 2020. This is a joint work with my colleague Lorenzo. Let's start by introducing the Farfalle construction. This construction was proposed at TOSC 2017. It is an efficient parallelizable permutation-based construction. It has mainly two kinds of components. The first one is permutations, including PB, PC, PD, and PE. The second is ruling functions like LFSR or NLFSR. From another point of view, this construction has three parts. The first part is mask derivation. The secret key is padded into a string and then handled by the permutation PB to generate the input mask and output mask key prime. The second part is the compression layer. In this part, the message M is divided into many blocks. These blocks are handled parallelly and finally compressed into one block again called accelerator. The last part is expansion layer. In this part, the one block accelerator is handled parallelly again to generate the output stream. As far as we know, there are two instantiations so far. The first one is Parity, which was proposed along the Farfalle construction. It uses the 6-round catch-up as its permutation and is fast on wide range of platforms. But the catch-up P has very large state, which limits it to apply on some low-end devices. In order to solve this problem, another instantiation, Xoofff, was proposed 1 year later. It uses a neural permutation pseudo with state just 384 base. It is more fast on some platforms. Roughly, there are three attack strategies. The first strategy is that we focus on the whole construction and exploit the relationship between the message and output, the relationship between the input mask and output mask to recover the key. The second strategy is that we only focus on the compression layer and try to find clearance on the accelerator by using the message. The last stage is that we only focus on the expansion layer. Note that in this layer, all input Si comes from the same state S, and we know all output blocks, so we can use them to recover the key. In our work, we use this strategy. In short, in our work, there are two main results. The first one is that we proposed practical attacks on Xoofff with reduced 1 or 2 round pseudo. And the second result is that we attacked Xoofff with reduced 3 or 4 round pseudo by using the meeting in the middle algebraic attacks and linearization technique. Please note that all attacks are independent with the compression layer and have been verified by experiments. Before introducing our attacks, let's see the specification of Xoofff. The permutation used in Xoofff is pseudo, and its states has 384 bits, and it is three-dimensional. Along the x-axis there are 4 bits, and along the y-axis there are 3 bits, and along the z-axis there are 32 bits. There are also 5 special notions. These 32 bits compose a line, and this is a plane. The whole bits compose a state, and this is a sheet. These 3 bits compose a column. Pseudo has 6 rounds, and each round has 5 steps: zeta, row west, iota, hey, and row east. The first step is zeta. From the expression we can see the zeta is linear operation, and one bit of input here affects 7 bits of output. In reverse, 1 bit of output is decided by 7 input bits. Row east and row west are just shifting operations along the x-axis and the z-axis. For example, row east, on the first plane there is no shift, and on the second plane every bit will shift along the z-axis by 1 bit, and on the third plane every bit will shift along the x-axis by 2 bits and shift along the z-axis by 8 bits. The only nonlinear operation in the round function is hey, and this hey is similar to that used in the catch hack. But the difference is that here the hey is operated on 3 bits instead of 5 bits, and the degree of hey is 2. Since we only focus on the expansion layer, so we only introduce the ruling function in this layer. From the expression we can see the ruling function is unlinear. This part. Please see this example. Si is the input of ruling function, and si plus 1 is the output. We can see 2 things from the transform. The first one is that the order of planes are changed, and the second one is that only the value on this line marked by green is changed, and it only depends on these 3 lines. Now we will introduce the attack on Xoofff with 1 round pseudo. By deep observation on the ruling function, we have found a weakness. Sum Si is the initial state, and Si plus 3 is is the 3-time ruling function on Si. There is a strong relationship between Si and Si plus 3. In detail, that is, this shade equal to this shade equal to this shade, and this shade equal to this shade. With this weakness, we found a distinguisher on one round pseudo. That is, after zeta, rho west, and iota, we found that the lines marked with the same color has the same value. For example, this line is equal to this line. Based on this distinguisher, we can do attack on Xoofff. The whole attack can be divided into 32 independent parts according to the value of z, and for each z, we can use 3 steps to recover 12 bits of k. In step 1, we can use the distinguisher. The bits marked by the blue color to recover 6 bits. And in step 2, since we already know 6 bits on this column and this column, so we can directly calculate another 3 bits on this column. The last step 3 is similar to step 1. We can use the equivalent on the line marked by orange color to recover the last 3 bits. Until now, we can recover 12 bits k for each z, and next we do the same attack on other z, and finally we can recover all k bits. In practice, with the 15 values of output CI, the success rate to recover all k bits is larger than 80%. Okay, let's move to the attack on 2-round Xoofff. In this attack, we use 2 different kinds of distinguishers. The first distinguisher is like this. After the iota in the second round, there is a strong relationship between 2 states. That is, this line plus this line equal to this line plus this line. Okay, with this distinguisher, we can do attack to recover some k bits. And this the whole attack can also be divided into 32 independent parts according to the value of z. For each z, we can choose many pairs of output CI plus 3, and check if all pairs satisfy the distinguisher. If so, the 9 bits k we guessed is the right k. Please note that there are always 2 candidates of 9 bits k remained, 1 wrong and 1 right. After 32 repeated processes for all z, there are 2 to power 32 candidates for this 288 bits k. In other words, with this attack, we can recover 256 bits information. Then we move to the second distinguisher. First, we introduce a new definition about parity. A parity on one line is the sum of 32 bits in the line. With this definition, we deduce a lemma, that is, the input and output of zeta has the same parity property. That is, for example, the parity on S00 equal to the parity on T00. The parity on S01 equal to the parity on T01. Yeah, with the parity, we found the second distinguisher on two-round Zulu. After the iota operation in the second round, we have another relationship between two states. The parity on lines marked by the same color are equal. For example, the parity on this line is equal to the parity on this line. So with this distinguisher, we can do attack on the Xoofff to recover the remainder k-bits. Firstly, we should filter out all wrong candidates remained in step 1. We just use the equivalent parity on this line and this line marked by the blue color. For each pair, we can build a linear equation. And with many output pairs, we can build a linear equation system. And in this system, there are only 32 unknown bits involved. So we can solve the equation system by Gaussian elimination. Until now, 288 bits, k-bits are recovered. With the same idea, we can recover another 64 k-bits based on the parity marked by the orange color. We can also build an equation system, but we found that each equation has the degree of 2 and is harder to solve the system than just a linear system. Luckily, we can sum two equations based on two different output pairs to produce a new equation, and this new equation becomes linear. So we can solve this linear by the Gaussian elimination again. In order to find out the last 32 bits k, we set up a system of linear equations with such form, and in this system there are only 32 unknown bits involved in it. Until then, we can recover all k-bits. The whole tag has been verified in practice. Totally 73 output blocks are enough to achieve a success rate greater than 85%, and the mean time complexity happens in the step 2 and is about 64 to power 3. The same idea can be applied to attack on Xoofff with 3 or 4 round Zulu. We can build an equation system and solve it, but the system has the degree greater than 2, so it's hard to solve it. In order to solve this problem, we introduce the linearization technique into it. Generally, if there are n unknown variables in the expression with degree at most d, the number of monomials in this expression is at most s and d in this equation. So we can add new variables to replace all monomials degree with degree larger than 1 to turn the nonlinear equations into linear ones. So we can solve it again with the Gaussian elimination, and the time cost is less than s to power 3, and the memory cost is about s to power 2. In this attacks, the distinguisher is like this. After one round, the lane marked by the same color has the same value. So there are 96 bits equivalent information for each pair. With this distinguisher, we can attack on Xoofff. In order to better understand the process, we start with the two-round pseudo. In the expression, there are 384 monomials of degree 1 and 384 monomials of degree 2, so we can use new variables to replace the monomials of degree 2 to transform the system into a linear one and then solve it. The same idea is applied on attack on Xoofff with 3-round pseudo and 4-round pseudo, so I drop this part. In the end, we summarize our attacks in this table. From this table, we can see that our attacks are independent from the compression layer, and they are the best key recovery attacks on Xoofff until now. That's my report. Thanks for your attention. Bye.